Welcome back. So we're starting a new part of the course, a new section. This is at least ostensibly on the syllabus that I wrote the last section. And this is the section which I entitled Active Matter, but I think it actually is kind of bigger than that. Maybe we should think of it as active matter, field theory, how to think about coarse graining, and that kind of thing. So this particular vignette is basically to orient us all towards what the big questions are. What are we thinking about? And here I refer to perhaps by 2105, and I hope you'll remember back to when I talked about David Mermin and the 100th anniversary of the big Einstein year. So people were looking forward to the future, trying to understand, what would we like to know in the year 2105? And so, my candidate was what the topics that we just talked about over the past few weeks, which is life as defiance, non-equilibrium. How are we going to think about systems that are out of equilibrium? But I thought this was a nice way to cast that problem. So that picture on the left is Stanislaus Ulam, who was a Polish mathematician who was famous for his work on using computers in the context of nonlinear dynamical systems, and his work on the hydrogen bomb. I don't know if that's a good thing or a bad thing, but that's the sorts of things. And by all accounts, very brilliant. And I really liked this comment from him. Using a term like nonlinear science is like referring to the bulk of zoology as the study of non-elephant animals. So Julien Thaler, who's shown here on the bottom bottom right, he was giving a talk, I think, at the Collège de France, and in that talk, he was focusing on non-equilibrium physics, and I appreciated so much this thing about non-equilibrium physics is like non-elephant biology, So he's paraphrasing and channeling the Ulam comment and quote, and I think that, that's really very important. And I like this quote also from Ulam: ask not what mathematics can do for biology, ask what biology can do for mathematics. I think that's very good. I think, ask what biology can do for computer science, ask what biology can do for physics. I have no doubt that biology can do a lot for physics. And so, but physics has got to get its house in order on non-equilibrium to be more helpful to biology. So, I just, to sort of pushing along that idea, make biology's gift physics one of them could be making us confront non-equilibrium. So, active matter. So, it's easy to forget that all the stuff that we see in the world around us is basically built up from the elements of the periodic table. Okay, yeah, it's easy to forget. It's not easy to forget. But the reason I say it's easy to forget is that there are so many different materials, So I just had a little piece of dessert, and so that led me to use a piece of metal and a piece of ceramic. This is my phone, it's got some plastic in it. It's got some metal, it's got some semiconductors, it's got all sorts of it's got some materials that are good at conducting thermal heat, etc. And the thing I wanted to say is that forever, basically, as long as people have been reasoning about it, the kind of matter that we call living has caused us some consternation. And it's clearly different from a hunk of rock. And the question is, what can matter do? And so, if you turn to a material science textbook, such as this classic one by Callister, which I remember very well from, decades ago, this book has sections on all sorts of different classes of materials. And we're living in this pandemic, and I have mentioned before that I love the third dimension. The third dimension means getting in airplanes. I love flying in airplanes, and one of the coolest airplanes is the 787 from Boeing, which is the first of the civil aviation planes, if I remember correctly, that uses ceramics in all sorts of ways that in the past we used metals. And the thing that's markedly missing from a book like this is the section on living matter, living material science. And it's not that I'm trying to make a field of living material science, it's just trying to point out that we don't have the mastery over the living part of the material world that we do over the non-living part. And what I mean by that is, if you go look up the sections on ceramics or on metals or on semiconductors, we really know a lot of stuff. We know a lot of stuff to the extent that we can be quite predictive. And, just to give you an example, the doping of silicon by phosphorus is a way to tune its conductivity in a very interesting way. And, what we're doing is we're engineering what's going on in the band gap between the conduction and the valence bands. And that's all great. And what I'm saying is that I dream for a time when our materials science books will have a proper accounting for living matter. I think I've mentioned this article before, and it's by Kirshner, Gerhardt, and Mitchison, and I'm going to mention it again now, and I'm even going to read from it again now, because I think that this notion of vitalism is not an opportunity for us to look with scorn upon our predecessors, but rather to look with sympathy upon our predecessors and with some humility to look upon our own circumstances, because truthfully, we're not on top of active matter. Like I'm going to...
Civetta has strayed up near the surface, even though it's broad daylight and hunters are on the prowl.
So, that's a school of fish, and here's starlings. And here's a herd of wildebeest. Okay, and those are three macroscopic examples, but I'm also going to show you the spindle and, the time evolution of the outer segments of our photoreceptors is another example of just a weird sort of activity at the level of the structure of cells and so on. And, I guess I would say, so let me read this comment from these guys. At the close of the 20th century, genetics reigns triumphant as the central theme in biological thought. The sequence of the human genome is widely seen as the starting point for biological investigation in the next century, and the debate on the origin of life largely defines alive as equivalent to accurately transmitting a genetic blueprint. We do not question the importance of genetics nor dispute the role of DNA as the blueprint for all the components of living systems, but we think it worth asking to what extent the post-genomic view of modern biology would convince a 19th century vitalist that the nature of life was now understood. And that's really the crux of what I want to say. Now, you could say, well, I don't care if I could convince a 19th century vitalist, but I think that would be a mistake. Because, again, people like August Weismann were not stupid, and I'm not saying that he was a vitalist, but, he was interested in, he looked and saw the motions of chromosomes and was trying to think about how that's connected to the sort of Mendelian genetics and so on. And, they're active, and how can one watch the partitioning of chromosomes and not be mesmerized and feel the mystery of it? So they go on to say, if the answer is not so close, will true understanding of living systems come from further annotating the database of genes, or must we explore the physical-chemical nature of living systems? In this essay, we discuss a few personal favorite examples, starting from blah, blah, blah. And so, I'm just trying to say that it's that I want to engage with in this final part of the course, which is the sort of, for the moment, the non-genomic aspects of what it means to be a living organism, and instead the things that were already hinted at and foreshadowed in the previous section on defiance, which is to say open systems with often in isothermal steady states, non-equilibrium steady states. What gives? How do we think about that? How do we write down theories? What kind of predictions do we make? What kind of measurements do those predictions suggest? What are the right experiments to design to get to the bottom of these things like active matter? So I won't rehash these examples, but here's the example of dividing cells in the Drosophila embryo. And the ballet that you're seeing before your eyes, the blue is the labeling of the nuclei in the form of DNA with DAPI, and then the green is the microtubules that form the spindle that does the partitioning of the chromosomes. And what I feel in some sense is that this speaks for itself. And if Galileo sitting in a cathedral watching the motion of a chandelier constitutes a worthwhile scientific endeavor leading to our thinking about the pendulum, if after that Huygens connects two clocks by a long rod that's connected by two chairs and sets one of them into motion and then finds the other one starts to swing and you get beating, if that constitutes legitimate scientific inquiry for the subject of physics, how on earth could this topic not be a legitimate scientific inquiry for the physical sciences? The answer is it can't. It is a legitimate topic. So So I just wanted to revisit a little bit. I mean, I think I've said this already, but I want to revisit just again now from the point of view of vitalism. You know, the kinds of things that caused people to say, ooh, this living matter stuff is just different. What's up here? So in 1774, Corti discovered cytoplasmic streaming, and I'm going to show you examples of this in the algae Cara later in the upcoming vignettes. But you know, the simple statement is that you look at these cells and you see, it would be like being up in an airplane looking down at a highway and seeing cars driving along. Just they keep moving along and along and along. So inside of the cell, basically what we see is the transport, for example, of chloroplasts and so on, and it's it's incessant. And clearly that was going to lead to people to try to think hard about, well, how does that work? And you know, we already talked about the paper of Robert Brown, but you know, that's another good example of looking at the world, this time through a microscope again, and realizing that there's the pollen particles originally, but also sphinx dust or whatever, it's just going to jiggle around. Again, giving kind of a little bit, of an impression of perpetual motion. And so the question is, what's up with that? I also think I mentioned biological electricity in the top. That is the work of Galvani, who was engaged in looking at frog legs and noting that he could inspire them to contract by applying a voltage effectively. These are in dead animals, and you know, then that's leads to questions about what's the nature of biological electricity. And then I already talked about the example of enzymes, so I think I won't repeat that. But just again, the debate between Pasteur and the Buchners about, you know, what is the nature of enzyme action. So the point of view of the Buchners was enzyme action is chemistry. There's molecules, they meet each other, they convert into other things, and that's it. But for Pasteur, the idea was that this is how a living organism makes a living. It's how it remains lifey. And they're both right. So what are the kinds of questions that we will attack? So, you know, I will be very excited about so-called biochemical reconstitutions, and probably tonight I will record a vignette that I will entitle The Real Biology, because I want to try to make a dichotomy between the biology that is and the biology that could be. It's not that I'm unaware of the role of evolution in dictating the biology that we see before us, but that does not convince me one iota that we should not constantly be on the lookout for examples where we can find the hydrogen atom of a biological problem and dig down into it so that when we come back to the real biology, we can nail it. So Zvonimir Dojic, now at UCSB, has done an amazing series of works in which he's reconstituted these cytoskeletal filament motor systems, and they form defects, and we will definitely think about what kind of continuum theories can be written down for these kinds of things. You know, you can see here that that there's a very beautiful opportunity for us to theorize on. This kind of follows on the heels of classic work by Suri and Leibler and Nedelec and Tony Maggs and others around a little before 2000, in which they also did these reconstitutions by looking at what happened when they used plus-in directed motors that were cross-linked, and then negative direction motors, and then et cetera. So the bottom line is that, you know, they're gonna prove to be a great challenge to us when we're wearing our theorist caps. And you know, I'm always excited about this Latin saying, hic rotus, hic salta, which I learned as a kid from one of my main teachers. And it concerns, I think it might be an Aesop fable actually, about a braggart who was on the island of Rhodes and apparently made a big jump across some long stream, across the stream. And he was bragging, and the person that was next to him said, "Here's your Rhodes, jump now. Hic rotus, hic salta." And the reason I like that is that, you know, who cares? You know, I don't want to hear, he was saying, I don't want to hear your story, just jump right here in front of me and show me. And what I feel like is that, you know, I'm not interested in jumping the entire stream of the entire complex behavior of a cell if I can't even understand what happens when we put together a few constituents, microtubules and motors and ATP or something like that. So I'll be excited about talking about that. And, we're going to try to develop a mentality like we did earlier in the context of gene expression for using knobs. I want to think of knobs that we can control both as experimentalists and as theorists. And I just wanted to give you a quick impression of some work that's going on at Caltech that was really driven by Tyler Ross, shown here on the left, and then Matt Thompson, shown here on the right, in which they figured out how to use light to optogenetically control the cross-linking of motors. And so in the presence of light, what happens is that now these motors cross-link, and so they dimerize, and that cross-links adjacent microtubules and leads to these nice, beautiful ordered structures like you see here. So this is a movie of the formation of what's called an aster. And so, there's a lot of different experiments that Tyler and Rachel and Hunjin and Matt and company did, Ziji. And, this is really fun and very interesting. And I would say it's grist for our mill to try to work out what sort of theoretical approaches will help us understand these things. This is, in a way, an homage to the classic David Rogers experiment where the neutrophil is chasing a bacterium. Here what you have is the aster chasing the disk of illumination. And so the bottom line is that, there's this disk of illumination, and that actually is where the cross-linking takes place, but there's already now a formed aster, and that's falling along this region of illumination. My last point is just to say, one of the things that we're going to do, we're going to be primarily in theorist mindset, and I'm going to try and set up continuum theory, field theories that allow us to describe elasticity, fluid mechanics, viscoelasticity, liquid crystal order, and then cytoskeletal motor systems. All of them with the intent of giving you an impression of what it means to try to coarse grain a system. And what we'll start with is elasticity. We'll go back to the horse's mouth. We'll go back to Hooke. This is a figure from his actual work, and we'll try to understand what is it that Hooke discovered in earnest. And what he discovered could be something that you learn in freshman physics about F equals minus kx, but it could be something more sophisticated, which is the relationship between stress and strain, which is much deeper in some sense, or at least more subtle. So we'll think a lot about elasticity theories, and we'll look at various dimensionalities, and that will give us an opportunity to revisit the continuum theory protocol, which I used earlier in the term in the context of diffusion. Now we will use it in the context of elasticity, in the context of fluid mechanics, and I hope it will be fun for those of you taking the course for credit. Indeed, there will be some drilling, some practice where I will try to get you to use the so-called indicial notation with the Einstein summation convention. It could be a little bit daunting at the beginning, but it's so incredibly powerful once you have mastery of it. So we'll talk about how to define field variables and how to, I'm going backwards, and how to think about things like strain and stress, and how to actually evaluate derivatives in a continuum and so on. And then that'll allow us to develop equations for the dynamics of elastic materials, equations for the dynamics of Newtonian fluids, and so on. So my dream let's be ambitious, for you all that are listening to this, for 20 years hence, after you've done your PhDs and your postdocs, the kinds of things that I hope you will work on will lead to a new chapter 16 in Callister, in which it will be the active matter chapter, and you might start off with the living periodic table, and then maybe, as a motivational, aspirational section, you'll give the examples from birds to chromosomes, and then you'll write down the balance laws and the constitutive equations. Those constitutive equations will be much more subtle and much more exciting in a way than Hooke's law, because they'll reflect the fact that energy is being consumed at small scales and percolating backwards up to large scales. And we would like to work that out. So that's our introduction to active matter. And what we'll do starting in next upcoming vignettes is we will talk about the actual, how we write down continuum theories.